Today we're going to be considering question 9, which says that show that a finite integral domain is a field. Take a couple seconds to try this out for yourself, then I'll give some hints, then we'll proceed the proof. Alright, for some hints, we will note that an important thing is we should recall what the definition of field is. And so once you do that, we'll note that for gunning, in a field, the set does not have to be a group, does not have to be an abelian group under multiplication, in the sense that you do not need commutativity of a multiplication. Some definitions you'll find online will require that, but that's a little harder to prove in this problem, and actually might not even be true. Instead, we're going to show, we're just going to show that it is a group under multiplication. And also recall what a definition of finite integral domain is, because that will satisfy many of the axioms of a field that we'll need. And we'll have to prove fewer things. All right, so for the proof, because it's a finite integral domain, we'll just look through the definition of the field and see how many that's satisfied. First, since we have a ring, noting that a finite integral domain is a subtype of ring, we know that since we have a ring, we have the associativity of multiplication and addition. We have the commutativity of addition, and some people require you need the commutativity of multiplication for a field, but we're not going to try to prove that here. Since we have a ring, we have the addition and multiplication of identities, namely 0 and 1, with 0 not equal to 1. We have the additive inverses, and we have distributivity of multiplication over addition, and we can also check if we get commutativity, then we can get addition over multiplication. Either way, what remains to be proven is the multiplicative inverse of any element. So let's try to prove that. To start, note that if you can ever prove this statement, a to the n equals 1, let's call it a to the m is equal to 1. If a to the m equals 1, then for all elements a, then you have inverses, since you let a inverse is equal to a to the m minus 1. Since if you multiply that by a, you'll get back 1. So our goal is to show that this exists for all elements. So with that hint, you can try to prove this yourself, with another hint being that you are going to try to prove this by contradiction. Otherwise, let's get right into the proof, which goes as follows. We want to show that a to the m is equal to 1, so we're going to go by contradiction and suppose that a to the m, there exists an element such that a to the m does not equal to 1. Now, how might this happen is an interesting idea. A to the m does not equal 1. Perhaps you could have something like the integers under addition, and you see those keep growing if you add 1 each time, but that we'll see violates the definition that it's finite. So somehow finiteness is necessary. Namely, that we're going to apply the pigeonhole principle, and the idea that, let's suppose our finite field has some set number of elements. Let's call that S elements. If it has S elements, then we'll have A non-zero, so we have a to the first. When you multiply by a, goes to a to the second, and dot, dot, dot. And so if for this element a to the m is never equal 1, then we know that we're going to get up to a to the s minus 1. And so that's using all the elements except for 1. And perhaps you should even limit this down to s minus 2, where we also want to ignore 0 and 1 because those are strange. If you get s minus 2, well, what would you do next when you try to go to a to the s minus 1? By the pigeonhole principle, we can't go to some element that's outside of our set, since we need closure, and we only have s elements. Therefore, we need to go back to some other element in our set. So let's denote this in a slightly different way. So just we're applying the pigeonhole principle that we have too many slots to fill, namely all of the powers a to the I, but we only have s elements to fill it with. And then we'll note that we don't actually just have s elements, we're trying to ignore the 1 case, and let's ignore the 0 case. Because if you ever get, let's address the 0 case. Let's suppose at some power, let's call it a to the k equals 0. Then, because this is an integral domain, This implies either a equals 0 or a to the k minus 1 equals 0. Well, we're trying to avoid a equals 0 since we started with we're trying to show that all non-zero elements have an inverse, and this is kind of a trivial case since we are going to suppose from the beginning that a is non-zero. That is, we want to show that all non-zero elements have inverses, so we need to show that a to the m equals 1 because then we can let a inverse be a to the m minus 1. So we had a non-zero, so this would be contradiction. Then we have a to the k minus 1 is equal to 0, and then by the zero product property again, we can get that a is equal to 0 or a to the k minus 2 equals 0. Since k is finite, we can repeat this process indefinitely until we eventually get a equals 0 or a equals 0, both of which are contradictions. Therefore, for no power is a to the k equals 0. That's an important result. So that means that these powers are not limited to just never being 1. They can also never be 0. Therefore, as soon as we get to the s minus 1 power, we'll note that the s minus 1 power must be a repeat. Since we only have finitely many elements to fill into these slots, we have s elements to fill into, we have s minus 2 elements to fill into s minus 1 element, into s minus 1 slots. Therefore, we must have a repeat at some point. That's the pigeonhole principle. So now that we've established the pigeonhole principle that eventually we have to come back and repeat, let's begin denoting some things. So this is kind of clunky to write a to the s minus 1. So let's write that as a to the m. A to the n. And let's let this element that it comes back to be the jth element, such that a to the n times a is equal to a to the j, or that's the jth element in this list. That means we can write that a to the n plus 1 is equal to a to the j. And this is kind of how we would formalize the fact that we have a loop somewhere. Once we have that loop, we're going to note that since we're in a ring, we have additive inverses, so we can pull the a to the j to the left. So we get a to the n plus 1 minus a to the j is equal to 0. And you can try to prove it from here, or we'll continue and let's see. We're going to now note that we can, since we have distributivity, since we're in a ring, we're going to factor out the a to the j term. So we get a to the j times the quantity of a to the n plus 1 minus j minus 1 equals 0. Now, we're nearly done because we have an integral domain, so either a to the j is equal to 0. We've considered that case, and that would imply that a is 0, but we're choosing non-zero elements, a contradiction. So our only other option is a to the n plus 1 minus j equals 0. A to the n plus 1 minus j minus 1 equals 0, since we have to have that the product is 0. So we can use the additive identity again. We get a to the n plus 1 minus j is equal to 1. What does this prove to us? Well, we'll recall that n is simply being s minus 1, and j is some element less than n, and less than s minus 1. Therefore, n plus 1 is going to be s, so this is a to the s minus j. J is clearly less than s, since we've shown that there's a loop backwards, then there's not really any way to loop forwards. Therefore, a to the s minus j is some element less than s. So we get that a to some power, let's call this L, a to the L is equal to 1. But this is a contradiction, because again, we're supposing that a to the m is never equal to 1. Therefore, since we're supposing that a to the m is never equal to 1 for any value of m, we have a contradiction, since we've shown that a to the L less than s, is equal to 1. And also note that m you can also bound in similar ways. So we have a to the L is equal to 1. So our supposition was false. Therefore, all that remains, we have a contradiction. Therefore, it must be the case that for all non-zero elements a to the m is equal to 1. And therefore, that every non-zero element a has inverses. And there, now that we've shown inverses, we have a field. With that, we'll just recall that some people might want you to prove commutativity, but for this problem, we are not proving it. Now we've proven, without commutativity, we've proven that every non-zero element has a multiplicative inverse. We are done. Thank you so much for watching.